Good morning, students. I am Professor N.V.S.N. Sharma. In today's class, we are going to discuss a variant of a standard radar which is used to continuously observe the locations of an incoming target, that is a tracking radar. So, in this class, we shall see what is the basic operating principle of a tracking radar, what are the types of radars available, what are the techniques used to improve the target detection, and some examples of tracking radars. Before we go into the details, first let us enumerate the functions that can be done using a radar. As we already know, a normal radar can be used first to identify whether there is any target or not. Then we can also find its distance from the radar, that is range. This is measured normally from time delay of the pulse transmitted to the echo received. The second parameter that can be measured using a normal radar will be velocity of the target. For this, we take the help of Doppler frequency shift between the transmitted and received signals. The third one that can be done with a normal radar will be azimuth and angle information. This is obtained from the antenna pointing direction. The antenna is placed over a compass, and the way the antenna is moving in the horizontal direction and in the vertical direction will be indicated through a pointer on the compass to get this angle information. Normally, azimuth information is sufficient, but there are cases where we need both azimuth and elevation informations. The modern radars are designed to detect the shape and the type of the incoming target. For this, the echo signal is processed separately and we get these informations which will be useful to quantify whether the incoming target is a simple one or a complicated object or an unknown one. For this, we call the method as signature analysis or inverse scattering problem. By this, we are able to find the target size by looking at the magnitude of the return signal, and the return signal direction can be used to identify the target shape and components. From the modulation of the echo signal, we can also find what type of moving parts are there, the type of turbine blades or the helicopter rotor, etc. can be classified from this data. And there are much better radars which can be used to identify the material composition of the targets. Before we go to the details of this tracking radar, let us first understand the new term, that is slant range. From the figure, you can see the inclined distance from the antenna to the target is known as the slant range, and as the antenna is rotating, you can see there will be some change in this value. In this diagram, you can understand how azimuth angle is measured. As we see from this, normally azimuth angle is measured from true north, and in the next slide we are seeing the elevation angle measurement. So it is measured from the antenna looking direction to the horizontal, the angle between them. Now let's get into the operation of a tracking radar. First, let us see what are the things we can do with this. It measures the coordinates of the incoming target and provides data to determine the target path. This will be highly useful in the missile tracking and missile guidance systems. Similarly, in the space applications, to locate the future positions of the satellite, then tracking can be performed in range, angle and Doppler, that means velocity. So we can concentrate on either range or angle or both, and in certain cases we concentrate on the velocity. Then the tracking radar is generally of two types. One is continuous tracking radar, the other one is track while scan radar. A tracking radar which is solely locked onto a particular target to give the coordinates of that particular target on a continuous basis is known as continuous tracking radar. This will be very expensive if multiple targets are there, because we have to go for so many continuous tracking radars for each of the targets. The second option is track while scan. That means while a radar is scanning the entire area, wherever the target is present, it will dwell more time on that to give very precise data of the target and proceed further. So while scanning is going on, it will be tracking some important incoming targets. So this is a low cost option for most of the countries. So track while scan means while scanning is going on, tracking will also be performed by the same radar. Obviously, the accuracy will be less compared to the other type. A tracking radar basically requires some input, that is, whether a target is present or not already and in which direction it is present. So an acquisition radar provides this data first, and the tracking radar will be locked onto the target and it will be able to give the data of the target on continuous basis from them. So the tracking radar is a secondary radar in general, whereas an acquisition radar is a primary radar. In this figure, you can see the applications of tracking radar. One is in space applications to track the satellites. Then for missile tracking, that is to understand in which direction the missile is traveling presently and what will be its future position in such a case. This will be useful to eliminate the incoming missiles very efficiently. The third one is for missile guidance. If you want to guide a missile so that the missile will be able to eliminate the target at shortest time, then this tracking radar information will be highly useful. Fourth one will be instrumentation radars are used as tracking radars to get the information of the incoming aircrafts or large ships, etc. They will be very useful for the controllers to get the exact information of the incoming object and convey the same to the pilot. So now let us see what are the types available in tracking radars. The first and foremost will be single target tracker. This is for tracking a single target. So as only one target is always in the range of this, it will be able to give the required data at a very high data rate. So normally we will be satisfied if we can get about 10 observations per second. To lock onto the target and to be able to give the data of the target on a continuous basis, we require a closed loop servo system. And by this, we can try to keep the error between the target and the antenna loop direction very less. The second type of tracking radar available is automatic detection and track, ADT. Here, the tracking is done as part of the surveillance, and the rate depends on the time for the antenna to make one rotation. That means the antenna will be rotating at a high speed as in the case of a surveillance radar, but around the target location it will be made to rotate slow so that more pulses can be transmitted towards the target to get more accurate data of the incoming target. So it can simultaneously track a large number of targets. Please remember, the earlier one is meant for a single target, but here we have the option to be able to track multiple targets. So here a closed loop system is not convenient for this. The radar is not supposed to get locked onto a single target. Thereby it works on open loop system, whereas the single target tracker works on a closed loop system. Another type of tracking radar which is used in the modern world is the phased array radar. Here we can track a large number of targets simultaneously, and this tracking is done on time sharing basis. It combines the rapid update rate of a single target tracker with the ability of the automatic detection and track to hold many targets in track. It combines the advantages of the previous two types and eliminates their limitations. But only disadvantage is the cost of the system is very high. A track while scan is the old name of this tracking radar. That means while scanning is going on, tracking is also done. The present day name of this is the automatic detection and track. So by this we can understand that basically there are three types of tracking radars. One is a single target tracker, which is meant for tracking single targets. Next we have automatic detection and track, which can track multiple targets, and it can be used also as a surveillance radar. The first one works on a closed loop system and it can track only a single target. The second one works on an open loop system, but it can track multiple targets. So combining the advantages and reducing the disadvantages of both, we have the third variety, that is the phased array radar. Here simultaneously several targets can be tracked as though we are tracking them individually, the accuracy of tracking is very high. But the disadvantage we get is that the cost of the total system will be extremely high. Now, let us go into the operational principle. How do we go with angle tracking? When a target is approaching, the antenna is to be moved continuously to track the target. To determine the direction in which the antenna beam needs to be moved so that we are able to track the incoming object, a measurement has to be made at two different positions adjacent to the target. For this, the antenna is operated in difference mode wherein there will be a null along the bore side direction and there will be two main lobes on either side of this. Then this antenna pattern is placed in the direction of the incoming target. If the bore side direction and the target direction are same, then the two beams placed on adjacent sides of the target will be receiving equal amounts of signals, and when you compare them, the output of the comparator will be 0. If they are placed not exactly so, then there will be high signal in one beam and low signal in the other. So there will be a comparator output, and this will be given to a servo system. The servo system output will be moving the antenna motors in such a way that the error between the two received signals is 0. Then we can say the antenna bore side direction and the target axis are coinciding. So in this method, using two adjacent beams, we will be able to get angle information in one dimension. If we require angle information in two dimensions, that means both azimuth and elevation are required, we require 4 beams in all. That is, 2 beams for azimuth and 2 beams in the orthogonal plane for the elevation. The crossover of the 2 beams determines the bore side direction. The tracking radar has to position the 2 beams so that the target axis and the bore side are made equal. If there is more signal output when a beam is placed on the right than on the left with reference to the target, it means that antenna is to be moved right so that the left beam can see more target size and can give more output equal to that of the right beam. And if additional positions are taken in the orthogonal plane, another angle can be tracked. So, what we can understand is that the error signal generating methods must be accurate to have good accuracy of tracking. So for this, we have several techniques. One is sequential lobing. The second one is conical scan. The third one is simultaneous lobing or monopulse. Now, let us try to understand what are these 3 different techniques, and finally we will have a comparison. What is to be preferred for different cases. So in the diagram shown, the target is coming in a particular direction which we can say as the tracking axis, whereas the beam is having a different direction called beam axis. If they are different, as per the diagram shown, we have beam position A and beam position B. It means on either side of the target we are going to place the beams and take the return signals. So the return signal pulses are as shown in diagram A. Then if there is any mismatch between target direction and the tracking axis, as you can see, the beam A is closer to the target, whereas the beam B is a bit far off. So the return signals, if you try to look at, there will be disparity. From this diagram, beam A return signal is going to be large because it is close to the target, whereas the beam B return signal is going to be small as shown in the diagram B. So by this we can understand that the beam B must be moved closer to the target so that it is made equal to the return signal corresponding to the beam A. So in sequential lobing, the lobes are placed next to the target in a sequential manner. If you are going with only two lobes, you will get the information of one angle. If you can place two more beams in the orthogonal plane, then we can get angle information in the orthogonal plane. That means, as shown in the diagram, if you have four lobe positions A, B, C and D, you can get the angle informations azimuth from C and D beams, elevation from A and B beams. So here a single beam is switched between two squinted angular positions to obtain an angle measurement. The error signal is obtained from a target not on the switching axis. The direction in which to move the beam to bring the target on board site is found by observing which beam position has the larger signal. This was discussed with reference to the diagram earlier. When echo signals, the two beam positions are equal. The target is on axis and its direction is that of the switching axis. If orthogonal angle information is needed, two more switching positions are needed. So, two-dimensional sequentially lobing radar might consist of four feed horns illuminating a single reflector antenna. An improvement over this can be a single squinted feed which could be rotated continuously. If that is done, then what we are going to get is conical scan. In this figure, you are seeing how exactly conical scan can be done. So here we have a tracking axis and the beam rotating axis, what we call as beam axis. The difference between these two directions is the squint angle. So here we are going to continuously rotate the beam around the incoming target axis. For this rotation, we need special feeds. There are two types available. One is a rotating feed, the other one is a nutating feed. Let us see what are these two things more carefully. When the feed is designed to maintain the plane of polarization as it rotates, it is called nutating feed. You can see my finger as though the dipole placed before the reflector antenna. If this has to be rotated, you can rotate this in a circular manner keeping the vertical polarization like this. If you are doing this way, then this field is known as nutating field. A rotating field is one which causes the plane of polarization to rotate. In the earlier case, we are always keeping the vertical polarization of the field and rotating the field in this manner. But now, in the present case, we are going to rotate the antenna in an axis like this. So, at certain point, the field has vertical polarization. At another time, it will have horizontal polarization like this. Again vertical, again horizontal like this. It's going to be rotated around this. Then we call it as rotating field. You can see in this slide what is the comparison between these two types. A rotating polarization can cause amplitude of the target echo signal to change with time even for a stationary target on axis. So, you feel nutating field may be better, but nutating field is more complex compared to a rotating field. So, we prefer to use a rotating field wherein the dipole or the field will be continuously rotating and the plane of polarization is going to change. That is easier for the regular operation. A typical conical scan rotation speed might be in the range of 30 revolutions per second. It means in 2 seconds it's going to complete the one rotation around the target with several beams placed adjacent to each other. The same motor also drives a two-phase reference generator with electrical outputs at the conical scan frequency that are 90 degrees apart in phase. These two outputs serve as reference signals to extract the elevation and azimuth errors. Now, let us concentrate on the receiver. The receiver is a superhet receiver except for features related to the conical scan tracking. The error signal is extracted in the video after the second detector. Range gating eliminates noise and excludes other targets. The error signal from the range gate is compared with both the elevation and azimuth reference signals in the angle error detectors. From this, what we can understand is that in the superhet receiver, as we know, there will be a detector after the IF amplifier, which eliminates the carrier and gives the modulating signal output. So, we will have a video amplifier after this. That will be the error signal which is used to control the antenna rotation. Similarly here, the echo signals coming from different ranges are processed in different receivers. For this, we will have separate time domain filters which will be receiving the signals from different ranges. By this, we will be able to eliminate lot of unwanted signal from the stationary targets at different ranges. So, range gating eliminates noise, and the range information is obtained from the sum channel output of the antenna. These can be used as a reference so that azimuth and elevation angle information can be obtained by comparing the received signals from the sum signal in the error detectors. Let us understand some operational aspects. The angle error outputs are amplified and used to drive the antenna, elevation and azimuth servo motors. The video signal is a pulse train modulated by the conical scan frequency. It is usually convenient to stretch the pulses before low pass filtering so as to increase the energy at the conical scan frequency. To perform analog to digital conversion, pulse stretching is accomplished by sample and hold circuits conventionally. The same technique is being used here also. The PRF must be sufficiently large compared to conical scan frequency for proper filtering and avoiding inaccuracy of the angle measurement. The PRF must be at least 4 times of conical scan frequency, but normally we go with 10 times the value. We normally go with AGC, that is automatic gain control. It has the purpose of maintaining constant angle error sensitivity in spite of amplitude fluctuations or changes of the echo signal due to change in range. That means the output of the AGC is going to be a constant signal even though there are variations in the input. AGC is a negative current supplied to the amplifier to adjust the gain so that the input fluctuations are absorbed by the variations of the gain of the amplifier, and hence the output will have uniform value. In that sense, AGC can be considered as an amplitude equalizer. AGC is also important for avoiding saturation by large signals, which could cause the loss of the scanning modulation and the accompanying error signal. Here, the AGC will provide a very low gain to the amplifier, and thereby the output is within the saturation limits, and thereby still with large input you will be able to track the targets properly. The practical point here is the gain of the AGC loop at the conical scan frequency should be low so that error signal will not be suppressed by the AGC section. Only the unwanted signal is not amplified much. Here you can see how conical scan will have the output signal if the beam axis and the target axis are same. All target returns have the same amplitude under this condition, and there will be zero error signal. If that is the case, the antenna direction should not be changed, and here we say no action is required. In such a case, you can see the return pulses in the graph shown. A practical conical scan is shown here. As the antenna is rotated, you can see a large amount of signal at certain angular locations and reasonably small ones at other locations. The adjoining graph indicates these variations. Because of the rotation of the squinted beam and the target's offset from the rotation axis, the amplitude of the echo signal will be modulated at a frequency equal to the beam rotation frequency. The amplitude of the modulation depends on angular distance between the target loop direction and the rotation axis. The location of the target in two angle coordinates determines the phase of the conical scan modulation relative to conical scan beam rotation. This scan modulation is extracted from the echo signal and applied to a servo control to position antenna axis on target. So we require two servos, When the antenna is on target, the conical scan modulation is of 0 amplitude. So, here we will have a comparison between sequential lobing and conical scan in terms of their disadvantages. In the case of sequential lobing, angle accuracy can be no better than the size of the antenna beam width. Variation in echo strength on a pulse by pulse basis changes the signal level, thereby reducing tracking accuracy. The antenna gain is less than the peak gain in beam axis direction, reducing maximum range that can be measured. The disadvantages of conical scan are as follows. 1. The antenna scan rate is limited by the scanning mechanism, whether it is mechanical or electronic. It is sensitive to target modulation, mechanical vibration, and wear and tear due to rotating speed will also give rise to certain limitations. Simultaneous lobing with a single pulse, angular coordinates can be obtained. Maximum unambiguous range is limited only by pulse repetition frequency. And monopulse, if you are going with this, it is free of mechanical vibrations. Errors due to amplitude fluctuation of target echoes are greatly reduced. So, monopulse means with a single pulse you will be obtaining angle coordinate or even coordinates. It is defined as one in which information concerning the angular location of a target is obtained by comparison of signals received in two or more simultaneous beams. A measurement is done based on a single pulse, so we give the name as monopulse. But many pulses are employed to increase the accuracy. The accuracy is not affected by amplitude fluctuations of target echo. Out of the several types possible, most popular monopulse is amplitude comparison monopulse. What is this monopulse is? Slide 41. Amplitude comparison monopulse compares the amplitudes of the signals simultaneously received in multiple squinted beams to determine the angle. The required squinted beams are generated by two slightly displaced fields on a parabolic reflector. While the difference pattern is for angle measurement, the sum pattern of the antenna is used for range measurement. Signals received from the sum and difference patterns are amplified separately. They are combined in a phase sensitive detector to produce the angle error signal. The sum signal is used to get the range and the sign of the angle of the incoming target. Let us see what is this phase sensitive detector which is used in the case of the monopulse. This system contains a phase sensitive detector that compares two signals of the same frequency. So basically it is a non-linear device. The output indicates the direction of the angle error relative to the bore site. Though phase comparison is done, the magnitude of the angle error signal is determined by comparison of amplitude signals. How does a 2D monopulse work? What we mean is two-dimensional monopulse. That means it gives the information of both the angle coordinates with a single pulse. Here, let us first understand some new components that are used. One is a hybrid junction, and here the inputs are 2 and the outputs are 2 in this case. What are the inputs? The inputs from the feed horns will be given to hybrid junction. So, with the 2 inputs, there can be 2 outputs. One output is the sum channel, the other output is the difference channel. So, using these type of hybrid junctions in 3 numbers, we can get both angle and range information with a single pulse. If all the 4 received signals are combined, A plus B plus C plus D, then we get the sum signal used for range. Then, if you take the outputs of the feed horns, A plus C into one hybrid junction, B plus D into another hybrid junction, then the difference of these 2 signals will give rise to azimuth information. That means, first 2 channels are summed up, then the difference of these 2 sum channels will be used to get azimuth information. Similarly, another 2 channels are summed in one hybrid junction, another 2 channels are summed in another hybrid junction. The difference of these 2 outputs are taken from one more hybrid junction to get the elevation information. So as you can see, A plus C will give rise to the center point of the one set of feed horns. B plus D information will give rise to another center point. The difference between these 2 will give rise to azimuth. Similarly, A plus B and C plus D channels are summed up separately. Then these 2 are applied to one more hybrid junction to get the difference for the elevation information. So, we can say that we are going to use difference of the sum channels to get the angle informations. The hybrid junction in waveguide form or in microstrip form are shown in the diagrams here. Basically, they are magic keys or rat race. So, port 2 and 3 will be used to get the inputs, whereas port 1 and 4 can be used to get the outputs. One sum channel, the other one difference channel. In the context of this rat race, you can go with 1 and 3 as inputs, 2 and 4 as outputs, or vice versa. A complete block diagram of a monopulse to be used for 2 angle coordinates is shown in this slide. The antenna outputs are given to 3 different hybrids. One is for sum channel output, another one is for elevation, the third one is for azimuth. All of them are separately processed, and the azimuth and elevation error signals are given to servo motors to adjust the antenna location properly, and the range information is obtained from the sum channel. What are the precautions in this case? It is important that large relative phase differences do not occur among the 3 channels. A typical value generally tolerable will be 25 degrees of phase for proper performance. AGC is required to maintain a stable closed loop system for angle tracking and to ensure that the angle error signal is not affected by changes in the received signal amplitude. Practical issues are generally a Cassegrain reflector is normally used to place the microwave circuitry at the back of the antenna. Feed system can also be used. Feed system can be easily supported with this. The greater the squint angle, the better will be the accuracy of the angle measurement. What is the trade-off? The on-axis gain of the sum pattern decreases if the squint angle increases. So there will be range inaccuracies if you try to improve the accuracy of the angle measurement. Simpler and more compact feed system can be obtained by using higher order waveguide modes to obtain independent control of the sum and difference patterns. This is one case where a waveguide is used with the several modes propagating simultaneously. Normally we see that a rectangular waveguide is operated at a single mode, which is the dominant mode, that is TE10. But here we go with TE10, TE11, TE20, etc. to get sum and difference channels of the 4 feed horns simultaneously using a single waveguide. Now let us see another type of monopulse, which is phase comparison monopulse. 2 antenna beams are used to obtain an angle measurement in one quadrant. Here the 2 beams look in the same direction, whereas in the earlier case they looked at slightly different directions. Due to displacement of the antennas, the 2 received signals will have slightly different phases but same amplitude. But the phase difference will be quite small if the electrical spacing between the antennas is small. So angle information can also be extracted in a phase comparison monopulse by employing sum and difference patterns and processing the signals similar to the case of amplitude comparison method. An analysis of the sum and difference patterns for the phase comparison monopulse shows that a 90-degree phase shift has to be introduced in the difference signal so that output of the phase sensitive detector is an error signal whose amplitude is a function of the sine of the angle of arrival from the target measured with reference to the perpendicular to the 2 antennas. What are the limitations of this phase comparison monopulse? Effect of grading lobes due to wide separation between the antennas. Ambiguities in the angle measurement. So, to overcome these problems, a portion of the parabolic reflector is sliced off to reduce this physical spacing between the 2 antennas. Amplitude and phase comparison monopulses. What are the plus and minus points of these things? A total of 4 hybrid junctions generate some azimuth and elevation difference channels. Range information is extracted from the output of the sum channel after amplitude detection. The angular error signal is obtained by comparing echo amplitudes, which actuates a servo mechanism to position the antenna. The angle of arrival is determined by comparing the phase difference between signals from the 2 separate antennas. Antennas of phase comparison are not offset from the axis. Let us have a comparison between the 2 types of trackers we came across. In phase comparison, 4 antennas are placed in upward direction and its side lobe levels are high. Sequential lobing suffers more losses with complex antenna and feed system. Amplitude comparison has high SNR. It has higher precision in target tracking due to the absence of target amplitude fluctuations. Angle error in 2 coordinates can be obtained by a single pulse. Conical scan integrates number of pulses and then extracts angle measurement, but there will be opposite process in monopulse. That is, each pulse gives rise to angle information. For different pulses, we are going to integrate or take an average of this data. Whereas in conical scan, initially all the pulses are integrated, then the angle measurement is done. Let us compare about the SNR. The SNR from a monopulse radar is greater than that from a conical scan, since it views target at the peak of the sum pattern. In that sense, the SNR of a monopulse is 2 to 4 dB greater than conical scan. Accuracy. Due to the high SNR, the range accuracy is also high in monopulse. The accuracy is not affected by fluctuations in the amplitude of the echo signal. Both systems are degraded by the wandering of the apparent position of the target caused by glint. What is this glint? We shall see towards the end. It is basically noise. What type of noise? We shall see later. Let us compare again in terms of complexity. Monopulse is more complex of the two. Conical scan has to rotate or mutate the beam at high speed. The Cassegrain is a popular choice for monopulse. A space-fed phased array can implement monopulse by using multiple feed similar to Cassegrain. Let us see in terms of minimum number of pulses. A monopulse can perform on the basis of a single pulse. For a phased array, one pulse is sufficient. But normally, a number of pulses are usually integrated. The conical scan tracker requires minimum number of 4 pulses per revolution of the beam to extract an angle measurement in 2 coordinates. The monopulse first makes its angle measurement and then integrates a number of measurements to obtain the required SNR. The conical scan integrates a number of pulses first and then extracts the angle measurement. Susceptibility to ECM, electronic countermeasures, basically for jamming. Conical scan tracker is more vulnerable to spoofing that takes advantage of its conical scan frequency. That means the jammer sends a huge amount of signal at the conical scan frequency, which is a low frequency. Hence, he will be able to pump in good amount of signal and the radar can be easily jammed. And we know very well, it's not easy to change the conical scan frequency because the antenna is rotating by that and the servo motors are designed already for that. Hence, it is very difficult to avoid jamming in case of conical scan. It can also suffer from deliberate amplitude fluctuations. A well-designed monopulse is hard to deceive. The application. Monopulse trackers should be used when good angle accuracy is needed. When high performance tracking is not necessary, the conical scan tracker might be used for its low cost. So before we end, let us see what is this glint is. It is angle noise or angle fluctuation. It occurs with complex targets that have more than one scattering center within the resolution cell of the radar. A single point scatter, such as a spear, does not show glint, whereas in an aircraft there are several points of scattering and hence there will be glint. The greater the target in angle, the greater is the glint error. Here in this picture, you can see first missile guidance system to employ monopulse technique. It was developed in year 1953. Similarly, you know very well about the use of Patriots to counter the Scud missiles. So Patriots will have a phased array system which is used to track several targets simultaneously. You can see the details of Patriot air defense system in this slide. The monopulse or a phased array radar is used if extreme accuracy is needed. Its improved interference immunity, resolution, radar signal processing and angle accuracy made it imperative in all modern tracking or guidance systems. Thank you.
Yeah, the following are the answers for the questions on tracking radar.
How monopulse tracking radar is free of mechanical vibration?
How monopulse tracking radar is free of mechanical vibrations. In a conventional radar, the pulses are sent while the antenna is moving from one location to another location. So, the mechanical vibrations due to antenna moment will be contained within these transmitted pulses, and the echo is also having the same thing. On the receiver side, the received signals are first added together or integrated together, and then we get the information on the range or angle. So, the conventional radar will have the difficulty of these mechanical vibrations, whereas in the case of a monopulse, only one pulse is sent at a time, and when pulse is being sent, the antenna vibration doesn't come into picture, and the received signal of this pulse is processed and the information is directly displayed on the screen. So, the mechanical vibration doesn't come into picture for the single pulse case. When we are taking several pulses together, then only the vibration aspect comes into picture.
Try.
How the accuracy of monopulse tracking radar is not affected by amplitude fluctuation of target echo.
How the accuracy of monopulse tracking radar is not affected by the amplitude fluctuation of the target echo. The amplitude fluctuation of a target occurs because the radar looks at the target differently for different pulses due to its movement in a normal case. But in the case of a monopulse, the radar looks at the target at only once. So, whatever angle it has, that will be processed and you are getting the display of that. So, there will not be any amplitude variations of the target.
Why is the echo modulated by conical scan frequency?
Why is the echo modulated by conical scan frequency in a conical scan system? It is due to the rotation of the squinted beam of this antenna system.
Why do we use several pulses though a single pulse is enough in monopulse?
Why do we use several pulses though single pulse is sufficient in case of a monopole? Yes, by the design, a single pulse is sufficient to get the information on the range as well as azimuth angle or elevation angle, or both, depending on the capability of the monopulse. That's how the name has been given as monopulse. But with one pulse, whatever data we get will not be very accurate. So, to get more accuracy of our information, we normally send 3 or 4 pulses towards the target at a time and try to process the signals after the data is established.
Why do we need AGC in a monopulse system?
That's it. Why do we need AGC in a monopulse? AGC is always required to stabilize the receiver chain. So, here also we use the AGC to have a stability of the receiver closed loop feedback system. This is very much useful for the angle tracking and to ensure that the angle error signal is not affected by changes of the received signal amplitude. Thank you.